Good afternoon, everyone. I'm Hao Huang, Assistant Professor for Social Sciences, and welcome to Illinois Tech Social Sciences Great Problems, Great Minds Seminar Series. Before I introduce today's speaker, I would like you to know you can submit questions during the webinar by typing in the chat box. We will open the floor to questions at the end of the webinar. Now I will introduce today's speaker, Dr. Dapeng Li. Dr. Dapeng Li is an assistant professor of geographic information science in the Department of Geography and Geospatial Sciences at South Dakota State University. Dr. Li holds a PhD degree in geography from the University of Utah, a master's degree in cartography in the geographic information systems from Peking University, and a bachelor degree in geographic information systems from China University of Geosciences at Beijing. His research interests include GIS and its applications in hazards, public health, transportation, sustainability, and agriculture. He is currently working on data-driven wildfire evacuation modeling and planning in the American West. The WebGIS applications in wildfire evacuation, public health, and agriculture, and also the wildland-urban interface and wildfire risk mapping. He has published more than 30 scholarly articles on these topics in top journals, such as the International Journal of Disaster Risk Reduction, Applied Geography, and Computers, Environment, and Urban Systems. His research has been funded by NSF and the state of South Dakota. His teaching focuses on GIS. He's also a certified GIS professional. It's very delightful to welcome Dr. Dapeng Li.
Okay, thank you for the introduction, Hao. It's an honor to be here and introduce my recent work. I have been working on wildfire application for like 12 years. I started this now research like in 2011 when I came to the US. Even now, I still have a strong interest in this now research. In this presentation, I will talk about some preliminary results from a current project. And this project is about developing data-driven wildfire evacuation plans, like for a community in Northern California. This is the outline of my presentation. Before I talk about like our research, our current project, I want to talk about like some background information about wildfire evacuation, because this audience might be from the Midwest, and maybe you are not familiar with this topic. And this slide shows the top 20 most destructive fires in California. And if we check the date, we can see like many fires they were in the past like a few years. Yeah, for a long time, like this fire, yeah, now number 3. For a long time, it was the like most destructive fire in California, but like in 2017, the top fire became the most destructive one, and later, like in 2018, the Camp Fire, which destroyed like over 18,000 structures and killed like 85 people. This one is the most destructive fire in California history now. So wildfire is a huge problem in not only in California, but also in many other states like Oregon, Washington, and like, yeah. And every year, many people were evacuated. Yeah. And many people could die like in those fires. And it's very important that we study wildfire evacuation so that we can develop a better understanding of how it works and how to use wildfire evacuation models to create like some better evacuation plans so that we can maximize public safety in future wildfire evacuations. So why does like California have so many wildfires? And these pictures, they were taken by me like in 2015 in August in Julia. This is in Southern California. Julia is a small town to the east of San Diego City. It's within San Diego County. And if you look at those houses in here, you can see they are surrounded by a huge amount of very flammable vegetation. Yeah, and the grasses in here, they are very dry, like in August. So when a fire like happens in this area, we need to figure out how and when to evacuate all the residents. Otherwise, they wouldn't survive. I mean, if the fire like approaches the houses. So how do we model wildfire evacuation? And this is a conceptual diagram. So this red line in here, there are the fire perimeters. This is the fire ignition, and the fire will spread towards the community in here. And when the fire approaches the community, we need to figure out when to evacuate the residents. And once the fire reaches the community, if the residents are still in here, they could die in the fire. So we need to study how this process works. And in wildfire evacuation modeling, we need to study how to use computer models to represent and reflect the real-world evacuation. So in a previous study, we used wildfire evacuation trigger points to study wildfire evacuation timing. And how does it work? This slide shows the mechanism. So we could use fire spread modeling to derive the fire spread rates in the landscape. And based on the rates, we can create a buffer for this community. And when the fire crosses the buffer, we need to evacuate the residents in the community. And the buffer is created using an input, the time, as the input. This one is a 3-hour buffer. And in this case, when the fire crosses the boundary of the buffer, the residents will have 3 hours to safely evacuate to another place. So in wildfire evacuation, some early research, it was based on pure traffic simulation. That was early this century, 20 years ago. And later, researchers started to use fire spread modeling in wildfire evacuation modeling. And it was characterized by this line of research called protective action triggers. And some recent trends, researchers have started to use different models to integrate different models. For example, the fire spread model, the traffic simulation model, and the trigger model into one coupled model. In this way, we can better understand the mechanism behind wildfire evacuation. Another recent trend in wildfire evacuation modeling is interdisciplinary collaboration. And we found out wildfire evacuation is very interdisciplinary. We need to have the knowledge and skills from many disciplines. And this slide shows a conceptual diagram for modeling protective action triggers in environmental hazards. So if we are to model triggers, we need to consider many factors. For example, if we are to model triggers in wildfire evacuation, we need to consider the natural factors. These ones, the weather, the landscape, the topography, they will all affect fire spread rates in the landscape. People's evacuation behaviors are also very important. These are about the social factors. And lastly, the built factors, the roads, the shelters, the warning systems, and so forth. These ones, they will affect evacuation traffic. And we need to pay attention here because those different factors, they are studied by researchers in different disciplines. For example, the fire spread modeling, many people they are in mathematics or physics. They construct models of spread of the fire in the landscape. And also like GIS is also used because a lot of data, they are spatial in here. Yeah, like the vegetation data, topographic data, they are spatial. The social factors, they are mostly studied by social scientists. For example, sociologists or psychologists. Yeah. They do a lot of surveys, household surveys to study people's evacuation behaviors. And the build factors, they are studied by like engineers, could be computer engineers or civil engineers. Yeah. They develop models to simulate the evacuation traffic. So in order to like model evacuation or study evacuation, we need to include all those aspects. So this topic is very interdisciplinary. In a previous study, we used is an open source software called like MetaSim. Is activity-based, also agent-based traffic simulator. And it can simulate every activity each person does in a day. And we can use it for evacuation purposes. Yeah. And the outputs, we can see it can give us a very detailed trajectory of each person in the evacuation. And this is a flowchart of like coupling different, like how to couple different computer models, like the fire spread model and the traffic simulation models to set wildfire evacuation triggers in a previous study. We can derive the evacuation time estimates, which is how much time like a community will need to travel to a safe place in the evacuation. We can derive the time from traffic simulators. From fire spread modeling, we can derive the fire travel times in the landscape, like when the fire will reach each location in the landscape. And we can also have the fire parameters as well. And for trigger modeling, we can use the derived evacuation time estimates and the fire spread rates in the landscape to set the triggers, which are the trigger buffers around the community. And then we can use like some computer programs to analyze the derived like vertical trajectories from traffic simulation, the derived trigger buffers from trigger modeling, and the derived fire parameters from fire spread models. And then eventually we can study the spatial temporal patterns of evacuation traffic and fire spread. In the previous study, we used like Julian, California as the study site. And this is a small town in San Diego County in Southern California. And this town has like 3 major egresses. And in the case study, we assumed that all the people will use this one because the fire is in here. It can close this tool. You need to close this tool because the fire can cross this two routes. If people use this two routes to evacuate, they can be trapped in the fire. And the points there are the households, household locations. Each household the traffic simulator will generate some cars for each vehicles for each household. The cars will travel in the road network. Go to the egress to get out of the risk area. And we consider only 2 simple scenarios. In scenario 1, we assume that the mean number of vehicles per home is 2. And in scenario 2, the mean number of vehicles per home is 4. Because nationally, the average number is maybe 2 to 3, but we don't know the exact number. So we consider the 2 scenarios in here, 2 and 4. And all the households in here in the town, their departure time distributions are in here. We assume that it's a normal distribution. All the people will leave within 80 minutes after they receive the evacuation order. And we created a series of trigger buffers for the for the town, for the town in here. And they are in different colors. And the smallest one is T25, which is like created like using 53 minutes. Yeah, this means 25% of the people can get out of the town within like 53 minutes. Yeah, so it's smaller, the buffer. The larger buffer is like 160 minutes in here for scenario 1. So it means 95% will be able to get out. Yeah, if we use like we have like 160 minutes for the evacuation. So when a fire reaches like the boundary of the buffer, if we send out an evacuation order, and if all the people their evacuation is like based on this departure time distribution, 95% should be able to get out. Yeah, that is how it works. And then we used a the fire spread model to simulate the spread of the fire in the landscape. And this shows the fire perimeter in here. And the numbers in here, they are in minutes. And the ignition is in here, ignition point is in here. And we can see the wind direction is south, from the south. Yeah, the fire perimeters like they are skewed along the wind direction. And this is like a trigger buffer in here, like 88-minute buffer in here. And then we use different like trigger buffers to test if the trigger buffers are effective. Yeah, and it turns out it really depends on the trigger buffer used. For example, in here, if we were to use the T25, in scenario 1, and when the fire reaches the community, 25% were able to get out. The other 75% they are still en route. And we can see the evacuation traffic in here, they are very close to the fire front, which means this one is not very good, because these people can be trapped in the fire and die. So if we use a larger buffer like T75, and we can see it's much better. The evacuation traffic is in here. It's about like maybe 2 kilometers from the fire front. It's relatively safer compared with this one. So this study shows us it's important to integrate those different models to study wildfire evacuation. And especially if we can map out the evacuation traffic and the fire spread over time, it will be very valuable for evacuation decision making and planning. So before I talk about a recent study, I want to provide some information about digital twins and its relationship between digital twins and wildfire evacuation modeling. So digital twins is very popular nowadays. So it's about like how to model a system to make your model like very close to the real thing in the real world. So this is the ultimate goal for any modeler. However, it's very challenging, because we have many issues in this process. Probably we would never be able to like get a model that can be perfect, copy of the real world. So in wildfire evacuation modeling, I think the largest challenge we face, in building a digital twin is data. We don't have enough data for building a digital twin for wildfire evacuation. So the past few like maybe 2 decades, we have seen like a lot of research done like in wildfire evacuation. Using big data, different types of data. For example, we can use like different types of data to map the diurnal population change. This is very important for evacuation research, because the population will change over time, like within a day. In different hours, the population won't be the same in one area. People's travel behaviors or evacuation behaviors are also very important in evacuation research. We can use like household survey data, which is a very traditional method. However, this one could be very costly, because every survey will cost us some money. And recently, people started to use like some new data, like for example, the cell phone location data, to study people's activity patterns and evacuation behaviors. The cell phone data, location data can be from the cellular towers, which could be very coarse resolution data, location data, or from like the GPS sensors on the smartphones, which can be very accurate. And another source is social media data. These data, they are all very important in evacuation modeling or planning because they can determine the evacuation travel demand. So before we use any type of data, we need to use some metrics to evaluate those data. So for example, to see if they are effective, they can be easily available, if they are accessible, scalable, and transferable. I think these are important like, metrics for us to evaluate if the data can be used in evacuation research. And here is like a brief summary of the different types of data we can use in wildfire evacuation modeling. And for some data sets, they can be easily accessed. However, for some other data sets, we can hardly get them. Yeah. For example, for GPS data on smartphones, yeah, it's very hard to get such data in the US because it's very sensitive and there are many privacy issues. And for population data, we can have some open data sets like from like the census and from the maybe some local governments. We can use some like structure location data as well, like the address point data. In some states they are open, in some states they are not. And the structure footprint data from Microsoft, this one is open data. For fire spread modeling, we need to use like weather data from the nearby weather stations. And we can collect the field model data and the topographic data from a land fire project, which is an open data initiative maintained by USGS. To do traffic simulations, we need to compile data like population data and home location data, household like vehicle ownership data. This one we can compile some data from census, the American Community Survey project, or we can do our household surveys by ourselves. And lastly, road network data. Many traffic simulators use like OpenStreetMap data. However, it is not that accurate sometimes because it's a crowdsourcing project. We can also compile some data from like US Census Tiger or from the local government. They have maybe the more updated data for the road network. And next, I want to talk about the recent study we did in the ISF project. And this slide shows a data-driven framework for modeling wildfire evacuation. We compiled like a large collection of data from different sources to model wildfire evacuation, to construct the model for a community, including the household vehicle ownership data from ACS and the home like occupancy type data from the town or Truckee, the local government, some road data from the local government and from the OpenStreetMap, and some weather data from the nearest weather station, some historical wildfire data, some fire behavior related data from the land fire project, some like spatial boundary data from the town or Truckee, and the residential parcel data from Nevada County, California. And the study site is in the town of Truckee. It's in the Sierra Nevada area in Northern California. And from Google Maps, you can see it's very close to Lake Tahoe. And there are many like ski resorts in this area. And many communities in here, they are resort communities. For example, like the gold medalist Eileen Gu in last year's Winter Olympics freestyle skiing. She was trained like in here in this resort. Yeah, and there are many resorts nearby as well. So it's and in the summer, many people in the fire season, many people will go there maybe to spend the time maybe in Lake Tahoe or nearby areas. So the issue is that in the fire season, if many second home owners or visitors like they stay there in the fire season, when a fire like happens, it would be very challenging to, evacuate those people because those people they might not be very familiar with the area. Yeah, so they may maybe make wrong decisions in the evacuation, and which is very dangerous. And we chose like one community in this town as the study site. It's this community. This is the largest one. And in this map, you can see like many homes in here. There are secondary homes. Yeah. The majority they are like secondary homes. Yeah. Some they are primary homes. And in the summer, like in the fire season, those second homes, many homes will be occupied by the homeowners, or some they are rented out to maybe the visitors. And this could pose a huge challenge for wildfire evacuation in this area. And the community only has 2 egresses, one in here and the other one in here. And we used like different types of data to construct a wildfire evacuation model and derive the evacuation time estimates for this community under different like circumstances. And the table shows like the composition of those homes, different types of homes. Primary homes only 21%, and the second homes almost 71%. Yeah, 4,000 like homes are secondary homes. And we did some like field surveys, field work, and collected some data for this sample in here. Yeah, so the homes in here. This is the sample. Specifically, we collected like the occupancy rate of the homes over time, and how many cars like each home has. And it turns out like in the fire season, the occupancy rate can range from like 37% to 58%. Yeah, 58% is this data point was collected on the 1st of July. That is the national holiday. So many people will, maybe second home owners will come here during the holiday. And like we can see in here on this day, the area will be, second homes will be heavily occupied. So the travel demand will change over time. This is why it's very challenging for wildfire evacuation planning. The average number of vehicles per home ranges from like 2.4 to 2.7 in those like in our data. So the overall like occupancy rate in the field work is from like 38% to like 58%. The corresponding like second occupancy rate of the second homes, they should be from like 20% to 50%. However, in the case study, we expanded the range to include like 10% and 60% as well. And we also included like 100%. In this case, we assume all the second homes are occupied. Yeah, this could be the worst case scenario. And these are the data points we collected in the field work. Yeah. And some data points there are in 2019, which is like pre-COVID, and 2020, and in COVID, and the data could be somewhat like abnormal because in COVID, I guess many people maybe chose to move to their second homes in this area, in this community. That's why like this one is like in here, like late June is much larger than that in the pre-COVID area, like period, like 2019. Yeah. More people moved to this community, I guess. Yeah. Based on the data, and we also collected some data from like the ACS, the vehicle ownership data, how many cars each household has. So the survey data, actually they only have like here, this one, 3 or more vehicles available. We only know it's like 35.2% in this town. This might not be very accurate, but this is the best data we can get for this study site. Yeah. So we don't know how many cars exactly in here in this category. So we made some assumptions, like 3.5 to 5. We'll assume like this is the maximum, number of cars per household for this group. And we computed the overall, like the mean number of vehicles for all the homes. It will range from like 2.1 to 2.8. And we use this as a parameter for our evacuation model. And this is the flowchart for the evacuation model. And we used like two parameters in here. One in here is the occupancy rate of the second homes from 10% to 60%. And we also included like 100%. And the mean number of vehicles from 2.1 to 2.8. And we use this number to randomly generate a number of vehicles for each home in the study site. And for this variable, we will randomly select like maybe say 10% of the second homes in the evacuation modeling. And for the departure time, we assume that like it's using this distribution. Yeah, these are in seconds. And this is a video. It shows us like how the evacuation model works. And these points, they are the cars generated at different like home locations. Yeah. And when the as we can see, when the evacuation starts, all the people will depart from the homes and to get out of the risk area using the two egresses. And some issues we found out is that we assumed that all the people will use the closest egress to evacuate. And if we look at the map, most people, they are closer to this one. So yeah, they will be using this one in the evacuation. However, this could be an issue because we can see like after like a few hours, these people are still stuck in here. And this egress is like underused, while this one is like maybe overused. Yeah. However, this assumption could happen in reality because many people in this region, they are second home owners. As I mentioned, they may not be familiar with this like area. And many visitors, they also maybe come to this area in the fire season as well. Like in the summer, maybe they will go to the Lake Tahoe, they will stay in this community. And this could be a huge challenge for wildfire evacuation modeling and planning as well. Yeah. And the evacuation travel demand will change over time. And the people's like evacuation, the behaviors, they can also be very important in evacuation planning. And this figure shows the derived evacuation time estimates from the traffic simulations. And it turns out like they will vary a lot for different scenarios. And the N means the mean number of vehicles per home. And the occupancy rate of the second home, they are in here, 10% to 60% and 100%. So all the previous studies, they assumed they are using they use normal communities. All the like homeowners, they are primary homeowners, no second homeowners considered. However, for such like resort areas, we need to consider the second homeowners, because if we don't consider the occupancy type, we can see it will overestimate the evacuation time for the community. And in reality, we only know the range like in here. For each day, maybe it should be between here and here. However, don't know if we don't have more detailed data, we won't be able to tell the exact or the more accurate like evacuation time for the community. And this is very challenging because we will need to use some very high resolution data, population distribution data for the community if we want to derive the more accurate evacuation time estimates. And some more results. These are for the derived time needed for 50% of the vehicles to leave the risk area. We can see it's much better in here, shorter times. And this one, the previous one is for like 100% evacuations, all the people to get out. And for an average of 2.1 vehicles per home, it could take over 10 hours if all the second homes are occupied. So the next step we did is to map out the vehicle count information at the road link level during the evacuation. And we mapped out the information for these scenarios. Yeah. For 6 scenarios. For the mean number of vehicles, 2.1, and the occupancy type, like 3 values in here, 10% all the second homes are occupied to 100% all the second homes are occupied. And the input time as well. Like when after like 80 minutes after the start of the evacuation, we map out the spatial distribution of the vehicles in the road network. And the results are in here. Yeah, on the left, this is for the n equals to 2.1. Each home, the mean number of vehicles per home is 2.1. And the occupancy rate in for A is like 10%, B is 60%, and C is 100%. And we can see like if we have like less evacuation travel demand, like we can see like fewer vehicles will be will be on route, and a lot of traffic will be concentrated in here in those intersections. If we have like more second homes like occupied, we will have more traffic, on route. And like in here, if 100% are occupied, like it will be even worse. Yeah. And in here, if we have more cars for each home, like on average, like 2.8 cars per home, we also have like, if we compare like C in here with this C in here, we will have more traffic on route in the evacuation. Yeah. Like in those on the road links. Yeah. If the fire like approaches, maybe reaches the community, and like those people, they can be trapped in the fire, or they could be maybe there would be a lot of smoke in the evacuation. They could have some car accidents or something. So this could all be very dangerous. On the discussion, as I mentioned, we still have like many issues with data. Yeah, several issues with data for now in terms of like wildfire evacuation modeling. The biggest problem is data availability. If you want to construct like an evacuation model for one community, you need to have the detailed like data for the community. For example, household like vehicle ownership data. If you use ACS data, because the sample could be biased, so it might be very accurate. It may not be very accurate for a community. In that case, we need to do household surveys. Yeah. Generally, it will cost maybe about $10 per survey package. So if you need to include maybe a few hundred like households, it will cost you a lot of money. Yeah. So we plan to do a household survey in this community so that we can have some more accurate data for our model. So another data source could be from like cell phone location data. It will be perfect for capturing the population distribution in the daytime, especially in the daytime. And we can also get the visitors' locations in the community. This cannot be maybe collected using household surveys because it's hard to reach them. Yeah, they will maybe stay there for a few days and leave. However, this data set is very difficult to get it in the US because it's very sensitive. It's about people's location data, and there are some like privacy issues as well. And the second challenge is the data management. Yeah. In the US, we are using like a very decentralized system to manage our data. Some very detailed data, they can only be collected from the local government. Yeah. Some open data, for the whole nation, usually are very scarce. Yeah. And many local government agencies don't have like a very good like cyber infrastructure to manage the data. It's very time consuming to compile all the data from different departments and construct a model. And in the future, we can use WebGIS to better organize our data, manage our data, so that we can, all those like stakeholders can use this data more conveniently. Another third challenge is model coupling. If we are to couple different models into one evacuation model, because they are implemented in different programming languages, it is very challenging. Yeah, it requires a lot of programming. And the first challenge is experimental design. Yeah, so if we are to use our evacuation model to create evacuation plans, how do we design those evacuation scenarios? There are so many possible scenarios. So, but we have like limited resources, computing resources. Could we consider all those scenarios or not? So this is a huge challenge for us. So how many scenarios should we include in our evacuation plans? If we have more data, we will have fewer scenarios. However, if we don't have enough data, we need to consider all the possible scenarios. And lastly, open science. This is about how to do science in a more open manner. So we need to like maybe incorporate not only like the stakeholders, but also the residents into our model, into our research, so that we can build better wildfire evacuation plans in the future. As I mentioned, people's evacuation behaviors, they are also very important. Yeah, we need to collect some more data from the like local residents, so that we can know more about the evacuation logistics and behaviors. Some ongoing research, this one research is quite related to this, is very related to our project. It's about like open wildfire evacuation modeling. We are trying to use open source tools, for example, like Sumo, MetaSim, and GraphGIS, Farsight. Those are all open source tools. And open data, like from sensors, from like ACS, from like landfire, and some data they are not open. Maybe we need to collect the data by ourselves, like household data, survey data. And we can integrate all those data and models to build a better wildfire evacuation model that can better reflect the real world. And the conclusion, from our preliminary research, we found out that the transient populations, they really pose a huge challenge to wildfire evacuation modeling and planning. And for the local resort communities, we need to consider many other factors. Those factors that were not considered in the past because no research were very little research was done like on those like resort communities. And the second one is that we need to consider like those occupancy type and rate of those residences in the resort communities if we are to do evacuation modeling or planning, because like those residences will be occupied very differently in different like maybe month or on different days. Even like within a day, it will be very different. And lastly, we still need to do a lot of work to better integrate different types of data into our wildfire evacuation models. Especially in the big data area, we have some new data coming out, and we need to figure out how to use those data to build better evacuation models and create better plans for our evacuation. So this project was funded by like the town of Truckee and the SDSU in the early phases, and it is being funded by NSF. And we are still working on this project, and we hope we can maybe incorporate some more data to create some a better model, and then we can use some other data sets to create some data-driven evacuation plans for this community in the future. And these are the key references. And any questions? Thank you for your attention.
I think Dr. Lee gave us very interesting talk about how to use the big data to create a more effective wildfire evacuation models for communities with transit population. And so currently, my question is, the first question is, in terms of this evacuation model. So I think we know for like a flood zone has like 100-year or 500 years flood zone. So I'm wondering like for the wildfire, if has this kind of 100-year or 500-year wildfire zone for people. So because for like a flood zone for these areas usually is not suitable for people living there, then for the planning, so people not living in this area. So I'm wondering like for wildfire has this kind of zone or not?
Actually, we don't have such zones in wildfires. I mentioned but we do have some data. For example, in here, like historical wildfire parameter data, we do have this kind of data. In California, they have some they do have some zones. It's called like fire security hazard like zones or something. Yeah, the zones they are based on this data. Yeah, but they don't have like a 100-year or something like that. Yeah, in flood wildfires they are more, maybe they are more frequent. Yeah.
But as you mentioned, like in California, hasn't this kind of zone is called, just now you said it's called like a wildfire evacuation zone?
No, fire hazard severity zone, I think. Yeah.
Oh, okay. Wildfire hazards security
Severity zones, I think. Yeah.
Oh,
Yeah.
severity zone. Okay. So like this kind of zone is also based on like the probability, the chance of people actually for this zone will got the wildfire hazards or not. Because for the flood zone actually is based on the chances. Like for 100 years, like is 1% chance, like this area will have this flood zone. So for that zone is also based on this probability chance or not.
Yeah, it's because like a flood and wildfires are very different. A flood happens like, if a flood happens like those low elevation areas will be flooded, right? So you can like do the prediction, like yeah, if you have the you have a flood model, say you can like predict, I mean which areas will be flooded. Yeah. However, wildfire, it can happen anywhere. Like in California, it can happen anywhere, right? We can only maybe do some like probability-based research to see which areas they are more vulnerable to wildfires, right? However, those ones they are based on the historical like wildfire data in many cases, or the vegetation data, topography, and so forth, such data. Yeah. And those zones like being used by California like fire hazard severity zones, how they derive the zones is not transparent. We don't know what algorithms was used. Yeah, it's like a black box. We have no clue what is going on behind the scene. Yeah.
Oh, okay.
So yeah, it's not transparent. Yeah, there's no paper or something or article about it. Yeah, how to derive the zones or what factors they considered or something. Yeah, but in generally we will use like wildland urban interface, right? To those zones they are based on the structures and the vegetation. Yeah, those areas they are like more vulnerable to wildfires in terms of like if you're in terms of structure loss or something. So we have such data. Those so protocols or algorithms for generating such data, they are open. There are many articles. However, for the zones used by California, it's not like open and transparent. Yeah, we don't know. The data they are available, but we don't know how they produce the data. And for some like insurance companies, I believe they have their own models to delineate the zones like that are maybe more vulnerable to wildfires, right? In California, they have their own model, but I think they are based on those data, like weather data, or like historical weather data, like historical like wildfire parameter data, and like vegetation data, like topography data, and so forth. Such data. If you have such data, you can build models to predict or model like wildfire risk. It's also like it's about the wildfire risk modeling. Yeah.
I see. That's very. It's kind of different from like a flood zones. It's based because a flood zone is like based on like conducted by like a FEMA, the government.
Yeah, but historical wildfire data that are also used in such models in most cases. Yeah.
I see.
But it's more complex than floods because a flood, it will flood the low elevation areas first and go up all the way to the high elevation areas. But wildfire, it can from any location. The ignition can happen at any location as long as it has like the field, right? The vegetation, you can have a fire from there. Yeah.
I see. Yes. So, then the other question is kind of following this is, for this evacuation zone, for this wildfire areas, it seems as you mentioned in recent years, this wildfire happens more often than before. It's become more frequent than before. But as you already list like 20 extreme events for the wildfire.
Yeah,
so
these ones they are about the most destructive fires. Means many, yeah, like there are some large fires, but they are if they are in the wildlands, they don't threaten like people, right? So they are not in here. Some fires they are only in the wildland, so it does not matter. They are not on the list. Here is about the structures, number of structures, and the people killed. Yeah.
yes,
I can see many there from the past like 5 years in here on the list.
so go ahead.
Like the 2020 fire season, like 2017, like 2018, yeah. These are many fires in California, yeah, and they are very destructive.
So then the question is, since these areas is become more frequent, but why people still, it seems the population grows in these areas. So why people move to these areas, people, even it's dangerous.
Yeah, because people like in here, this house, people want to have a good scenery, right? Have a good view when they look out the window. So that's why they would like to, live on the mountains or like in the forest. Yeah. And it's also maybe need some kind of like privacy. Yeah. So that's why, and they really have good views in here if you live in the wildland, right?
So
even though it's surrounded by like a huge amount of like very flammable like vegetation.
So I think that's actually related to the other question is it seems for your talk is for your research is mainly related. You mentioned it's for the estimation time is based on the vehicle, the number of vehicle per household, and also occupancy rate. So then I'm wondering, like you said, the people move here is because of the views. Then I'm wondering for the planning, for the urban planning, they would consider this file as one of the factors for their planning. Like if this is the fire pro communities, then their occupancy type or their land use will be different for zoning regulations.
Actually, yes, there are many issues, in urban planning. Because, for example, if like one community, if they want to build like a large apartment building, right? If they do that, there will be many residents in the building. All the residents, many of them, they will have cars. So there will be more evacuation traffic if a wildfire happens. And in that case, they need to do the evaluation to see, if they have the capacity to, safely evacuate all the people after the, this project, right? After they add the large like apartment building. I mean, if they can't, maybe in many cases they won't approve the project. Yeah, in some cases, yeah.
Okay.
So yeah, it's very important in such cases. However, in some other cases, so the real estate companies, they want to maybe build some houses in those very beautiful areas. They don't care about if it's fire prone areas or not. Yeah. So it's, yeah, in that case, they only want to make money, right? Yeah. People who buy the houses, they are willing to take the risk sometimes, yeah, because they know it's in a fire prone area. And in many cases, the insurance companies wouldn't sell insurance to them, to those homeowners, if the area they are in a very like high wildfire risk area.
I see. So, which means that as you just talking about the urban planning, they did consider these factors when they do like the land use planning or
yeah, especially when you want to add like some like large apartment buildings, right, to a community. This is, yeah, there will be a lot of debate, I mean, on this. Yeah. Many local residents won't maybe agree, yeah, because they are afraid there will be so many cars that could get stuck in the evacuation. Yeah. When a community only has like limited egresses. Yeah. And sometimes if they build more homes like in one community, they need to maybe build a new route as well as the egress, so that people can maybe, yeah, evacuate like maybe very quickly. Yeah.
I see. So since it seems that you didn't introduce in this talk about the occupancy type and variance by occupancy type. So I'm wondering, this is already in your current results, or is the future work you will do?
Occupancy type, we already included it in our model. Yeah, occupancy type. Yeah, we like actually when we constructed our model, these ones, right? When we say like 10%, it means we will randomly select 10% of the second homes in here, and they will generate the vehicles in the simulation. Because we don't know which 10% in here will be occupied, right? We don't have the data, so we can only run many simulation, do many runs, and yeah, in the simulation, and randomly select 10%.
I see. I see.
Yeah.
So,
we already considered this occupancy type, I mean, in our model. Yeah, second homes, like the occupancy rate for the second homes. Yeah. Primary homes, they are 100% occupied, right, all year long. Yeah.
I see. I see. And also here the unknown is some like missing from the survey.
Pardon? So
For the unknown. The
those ones, yes, because they are missing the data. Maybe there are some special homes, like, yeah, mobile homes or something. Yeah, so they are special. So these are vacant. We did consider these ones, yeah, as primary homes, yeah, mobile homes, yeah.
Okay. So then the other question is, it seems you introduced like two scenarios for the number of vehicles. One is 2 and one is 4. Wondering, did you also consider the demographic variation between these, or control the demographic variation between these two different scenarios? Like one is 2 cars.
Yes, that's in the previous study, right? In the previous study, this one.
Yeah.
This study actually, as I mentioned, we didn't do any like field work to collect more information. We made some like assumptions in here, because we do know like the national average. I mean, it's maybe between 2 or 3 or something like that. Yeah. The best data we can get is from like ACS. Yeah, actually, but it's not very accurate, as I mentioned. Yeah. without
Okay.
doing like a household survey, we can only make assumptions. Yeah. Compared with this study, our new study actually is more accurate. We do have some like field work done, right? So it's and we also like used like the ACS data to make the assumptions in here. This is the field work. We did the count, in the field. Yeah, it's a small sample. I sample all the homes in the neighborhood. Yeah.
Okay. Okay.
And
Thank
here we
you.
only have assumptions for here because we don't know the details for this category. Yeah, we made some
I
assumptions.
see. I see. Okay.
And this data in here is from ACS, from ACS, the percentage on this one, only this one and this one. And we did the math by ourselves in here.
Okay. Okay. Thank you very much to give us a very insightful talk about the verified models and how to help in verification planning. So usually we give the speaker the applause. Thank you so much.
Okay, thank you for the invitation.
Mhm.
Okay, bye.